Stage is yours.
Okay. Hello, everyone. My name is Landi Andrea Mapianina. I'm a PhD student working in the field of graph data management. I am from the Computer Science Research Institute of Toulouse in France and from the Activus Group company. So today, I'm going to present our work entitled Querying Temporal Property Graphs. So this was a joint work with my colleagues Franck Rava, Jifu Song, and Nathalie Vallès-Parlangeau. So first, let's start with the motivation of our paper. So in the real world, entities such as objects or people are interconnected in many ways. For instance, we can see on the left figure that people interact during their activities at school, at work, or on their social networks. So such activities generate interconnected data. Interconnected data are generally represented by property graphs. So we can see there a property graph. It is a data model that is composed of a collection of nodes and edges. And nodes and edges contain properties. So it allows for representing entities connected together by their relationships and described with attributes. Furthermore, entities and their relationships can evolve over time in many ways. So this evolution can be categorized in three types. First, the topology evolution. It means that entities and their relationships can be added and removed over time. So for instance, we can see on the left figure that the girl has a new relationship in orange at the second day. Also, we can find the evolution of attribute set. It means that the attributes describing entities and their relationships can be added and removed over time. So for instance, on the middle figure, we can see that the girl has a new attribute in orange to describe her. Also, we can find the attribute value evolution. It means that the attribute of entities and their relationships can be updated over time. So for instance, on this right figure, we can see that the attribute health status of this woman has been updated between the two dates. So the research question that we addressed in our paper is the following: how to model and query temporal interconnected data, including these three types of evolution. So to answer our research question, first we studied the modeling of temporal interconnected data in the literature. The property graph we see earlier cannot represent the evolution of interconnected data because it does not include the time dimension. In the literature, the classic modeling approach to capture changes in graph data is to capture the snapshot of an entire graph at a regular time interval, as we can see on this left figure. So this is called the sequence of graph snapshots. However, this classic modeling approach has several limits. First, it replicates data that do not change over time in graph. So it does not capture in an optimal way the changes in graph data. So it is not a scalable solution. Second, the data model based on this modeling approach are physical, so they lack of a conceptual view to meet the needs of designers and developers. And finally, this classic modeling approach does not capture the three types of evolution we mentioned before, so they do not provide a unified framework for designers and developers. So in response to these issues, we propose a data model completely in break with snapshots. More precisely, it consists in extending the property graph by redefining it with user-oriented concept and by introducing new concepts to capture the three types of evolution we mentioned before, and also to avoid data replication. To answer our research question, we also studied the existing solutions to query temporal interconnected data in the literature. So to do so, we identify three categories of solution. First, query language of graph database system, such as Cypher in Neo4j, to query property graph data model with a type dimension. Then we identified some extension of current graph query languages to support temporal analysis on graphs. And finally, algebraic operators to manipulate graph-based model that include temporal aspects. So we also defined, To evaluate these solutions, we used basic comparison criteria that we found in the literature. First, a solution must be composable. It means that a complex query can be decomposable into simpler ones to facilitate their understanding and their reuse. Then a solution should support basic graph operation to express analysis without time dimension. And finally, a solution must support temporal graph operation to express temporal analysis, so analysis on graph data with time dimension. We also decided to add 3 comparison criteria to meet the needs of designers and developers. So a solution must rely on user-oriented concepts instead of technical ones, such as one we found in relational algebra, like projection or selection. Also, a solution must support direct querying at all levels of the graph, that is, a single component or a set of components. So existing solution based on snapshot snapshot model do not allow to do so. And finally, a solution must be directly implementable in technical environment to facilitate their use. So as we can see on this table, no existing solution are covering all 6 criteria we said before. So our contribution consists in proposing standard operators for querying the evolution of interconnected data, and that covers all these 6 criteria. So now let's move on the details of our propositions. So first, we propose a conceptual model called the temporal property graph that facilitates the representation of the temporal evolution of interconnected data. So contrary to the classic property graph, we proposed user-oriented concept. First, we proposed the temporal entity concept. So a temporal entity corresponds to an entity of the real world and its evolution. A temporal entity is characterized by a label describing its semantic, also an identifier, and the evolution of the entity is represented by a set of states represented by nodes here. So at each evolution of the entity, a new state is created instead of overwriting its old version to keep track of its evolution. And each state corresponds either to the evolution of its attribute set or its attribute value, or both. So for instance, here we can see that between state 1 and state 2, the attribute vaccinated has been added, and between the state 2 and the state 3, the attribute status has been updated. Also, we propose the concept of valid time, which is assigned to each state. The valid time is a time interval assigned to each state to capture the occurrence of the changes and also their duration. In the same way, we have proposed the concept of temporal relationship. A temporal relationship corresponds to a semantic relation between 2 conceptual entities. So it is represented by edges on this figure. And a temporal relationships, the evolution of a temporal relationships are also represented by a set of states that are illustrated there by rectangles. So for instance, on this figure, the green part represents the evolution of relationships between 2 entities in terms of attribute value by the addition of a second state. And the blue part represents the evolution of topology by the addition of a new relationship between the 2 entities. So to sum up on our model, it meets the needs for modeling the 3 types of evolution we mentioned before, and it avoids data replication because we capture changes at the level of each entity and each relationship. So our second proposition consists in user-oriented operators to query temporal interconnected data. So these operators manipulate the concept of our temporal property graph model. On the one hand, we propose the predicate matching operator. So it allows for extracting state of entities and relationships from our temporal property graph by applying conditions on attributes and valid times. And we also propose the pattern matching operators. It allows for extracting state of entities and relationships of our temporal property graph that match a user-defined graph pattern. So to cope with the lack of existing solutions, our operator must cover the 6 desirable criteria we mentioned before. So to validate these 6 criteria, we will consider the use case of a dataset about the spreading of an infectious disease in a school environment. So in this dataset, there are students that represent entities illustrated by nodes, and their interaction represents the relationships between the entities. So students evolve in terms of their attribute value, and the relationships are evolving in terms of the topology. So new interactions are added and removed over time. So this is a representation of this dataset in terms of temporal property graph. So the first criteria was, is our operator composable? So for instance, if we make the following analysis on the previous dataset, are there healthy students that socialize with sick students? This analysis involves conditions on attributes of students, but also involve conditions on patterns of the relationships. So this analysis translates by the combination of the 2 operators. We include the condition on attribute on our matching predicate operator, and we include the result of our matching predicate in the matching pattern operator, plus the condition on pattern. Then our operators support basic graph operation. So what we meant by basic graph operation, they are operations that are used to express analysis on graphs with a time dimension. So basic graph operation include filter operator. It allows for extracting subgraphs from a graph without time dimension according to a condition on attributes. And also it includes the basic pattern matching operator, which consists in extracting subgraphs from a graph without time dimension and that match a user-defined graph pattern. So if we take the same analysis as before, are there healthy students that socialize with sick students? We can see there that our operator already includes the filter and the basic pattern matching operations. Then our operator supports temporal graph operation. In other terms, with our operator, we can express analysis with time-dependent information. On the one hand, we can make analysis on a specific point in time. So for instance, are there students that were sick at the 9th of May? But we can also make analysis on the evolution of entities and their relationships, that is on a time period. For instance, how did evolve the health status of the student Valerie since the 9th of May? So the condition on the time dimensions of this analysis are translated by the condition on valid times of students in our matching predicate operators. Our operator rely on user-oriented concept because it is based on our temporal property graph model. Last but not least, our operators support direct querying at all levels of the graph. Indeed, we have seen on the previous analysis that we can make a query on a single component of the temporal property graph, such as a single student. But we also can make a query on a set of components, such as several students. Finally, our operator must be directly implementable in technical environment. So to do so, first, our conceptual model of temporal property graph must be implementable in a technical environment. So to do so, we proposed automatic translation rules of our temporal property graph into the property graph model, and from our property graph model to graph database systems, such as Neo4j and OrientDB. So we can see in this table, for instance, that a state of a temporal entity in our temporal property graph corresponds to a node in the property graph model. So a temporal entity in a temporal property graph model corresponds to a set of nodes in the property graph model. Similarly, we proposed automatic translation rules from our two operators to basic graph operations, and from our basic graph operations to graph query languages, such as Cypher for the Neo4j graph database systems. So we can see, for instance, in this table that our matching predicate operator translates into the filter operator among basic graph operations, and the filter operator is translated to the where clause in Cypher, the query language of Neo4j. So now let's move on to the experimentation that we conducted to study the feasibility of a solution. So to do so, we used two datasets, a real dataset about a social experiment of disease tracing in a school environment, and a benchmark dataset about the transaction of a retail company. So both datasets include evolutions. We also used two graph database systems, namely OrionDB and Neo4j. Then we transformed both datasets into the temporal property graph representation, and we imported both datasets into Neo4j and OrionDB using our translation rules. So we also expressed some temporal analysis on both datasets, such as the one that we have seen in our previous example. We transformed this analysis into our operators, and then we translated our operators into queries expressed in graph query languages of Neo4j and OrionDB. And finally, we ran the queries on both graph database systems. So this experimentation has validated the feasibility of a solution, but we are currently pursuing this experimentation to evaluate the performance of our solution in terms of query run times. So to do so, we have created 28 benchmark queries that cover a wide range of scenarios of the temporal evolution of an application. So we classified these queries into 4 criteria. First, we can query at the level of a graph scope, so ranging from a single entity to the entire graph. The time scope ranging from a single time point to several time intervals. The evolution type in terms of attribute value, topology, and attribute set. And finally, the operation type, which refers to an aggregation or comparison. So to conclude on this presentation, so we proposed a new solution to model and query temporal interconnected data to cope with the lack of existing solutions. Our solution has several advantages. First, it provides both means to represent and analyze graph data with time dimension and to retrieve their evolution over time. Also, this solution is based on user-oriented concepts, so it provides a unified framework for designers and developers. This solution is directly implementable into technical environment, so it is easy to use. And also for our experimentation, we have seen that we can make real-world analysis with our solution. So for our future works, we have seen in this presentation that from our viewpoint, only basic graph operation requires an extension to meet the needs of temporal querying. But we agree that this intuition needs a future systematic study to confirm the completeness of our operator. And as I have said before, we are currently pursuing the evaluation of the efficiency of our solution. And this involves the proposal of several alternative implementations in terms of graph database systems, in terms of graph query languages, in terms of dataset, but also in terms of query types. So this is the end of my presentation, and thank you for your attention.
For starters?
No question about privacy. So you showed us the slide where you had the snapshots that were reported in the literature before. But when I understood your approach right, then you didn't go for the snapshot, but for some kind of a delta description, right?
Sorry?
So you didn't go for this snapshot approach. So your graph in the background maintains when attributes are active or not, let's say, right?
You ask if I have used the snapshot approach? Is that it?
Yeah,
Yeah.
yes.
No. I have not.
Yeah, it's okay. That was also my perception. But then I wonder, why did you disregard this snapshot approach? Was it for computation or?
Yeah. So in an earlier study that we have, in an earlier work that we have done, we have compared our approach to the snapshot solution. So we have seen that the snapshot is really bad in terms of scalability and also in terms of query run times. So that's why we choose to not use the sequence of graph snapshots. So there are many works already in the literature that show the limits of snapshots. So that's why we didn't choose this approach.
Yep, I'm asking because Dominic and I are at the moment supervising a master student who's actually elaborating on this, and he took the decision to keep both approaches. So on the one hand, he has the snapshots, and on the other side, he is maintaining this change information. And he says you can take both advantages, and Neo4j, for example, there's not really an issue with storage and stuff. So,
okay.
Not sure what now my question is, but yeah.
Yeah. Yeah, is that, yeah. In the literature, the snapshot approach is really suitable for networks analysis, for instance. But in networks, they are not a really big data set, so it depends on your data set, I think, also.
Okay, thanks.
Further questions? Nobody? Okay. So I would like to know, I mean, there are two aspects, right, that you also focus. One is the complexity of the querying, and the other aspect is also the capabilities of storing all of that information, right?
Yeah.
So what are the plans for extending this work in the future, having these two objectives kind of in mind?
Now you are testing alternative implementation of our model. So we want to check the translation of our temporal property graph into the RDF data model, for instance. So we will evaluate the performance in terms of query run times. And also we are working on the data exploration side of our model. If we can discover new insights with this structure of the graph. So we plan to test some algorithm like clustering, for instance, to see if we can extract interesting insight from this model. Yeah.
Okay. Yeah, so very explorative also.
Yeah.
I like it. Yeah. Yeah, I can only recommend getting in touch with the colleagues at University of Hasselt. I think there might be a nice collaboration upcoming.
Yeah.
Good. Final questions before we close early? No? All right, then thank you again for a very nice presentation to both authors, actually. Yeah, and enjoy the longer coffee break.